everyone, and good afternoon. Thank you for joining, and thank you for being here. My name is Kyle Rice. I'm the Midwest Territory Manager for STEINERT US, focused primarily on metal recycling. I'm looking forward to talking with you a little bit today about non-ferrous metals refinement. So we'll dive right in. The content's broken into two sections. First, what is refinement? We're gonna cover that question in detail, and you'll have a good idea of what it is and what we mean by that. In section 2, we're going to dive deeper into the products that you can produce, some of the qualities that you may expect, and what a refinement solution could look like for you. So as we look at this question, what is refinement? Refinement may be a word, or the way that I'm using it in this phrase may be something that's new to you. So at its base level, refinement is the process of producing higher quality furnace-ready products. Globally, we've seen a shift in scrap requirements. We see this shift to needing furnace-ready products. For example, Zorba today is not a furnace-ready product. It requires further processing. This further processing is a form of refinement as it's done today, and we're going to cover that in more detail. So refinement is the process of producing those higher quality furnace-ready products. And also at a base level, it's how you extract the maximum value from your material stream. So to break this down, we're going to have a look at this chart, and we're going to start with recovery. Really, it's broken down into two steps. This whole chart is recovery and refinement. And we're going to start at the recovery level because you can't refine your products without first recovering them. So as this chart is broken down, what you see on the left-hand side is the different levels and the aim of separation. What you see in the columns is the technology and the equipment that's going to help you do that sort. So the first three levels are recovery levels. Level 1, ferrous scrap recovery, performed with magnets, permanent and electromagnet. Level 2 is non-ferrous metal recovery, so the production of Zorba. Many of you are familiar, you're going to do this with an eddy current separator. Level 3 is recovery and upgrade of stainless steel, wire, boards. This is typically going to be done with an ISS induction sensor sorter as well as a KSS combination sensor sorter. So these three levels are where we're going to start because, as I mentioned, you need recovery to move on to refinement. So we're going to focus for a little bit first on the recovery levels. So what do these look like? We'll start with simple level 1. Electromagnet. So for primary ferrous recovery, primary steel recovery, you're typically going to see a large electromagnetic drum like you see here. The trend today is typically moving towards more electromagnetic drums in line. A general layout is probably two, one primary recovery, one as a cleanup step to remove any entrapped rags or material. Overall, you can also use other magnetic products, say on your ASR outfeed. It's very common to have an overband magnet, a permanent or electromagnetic there. And this is really the summation of level 1, using magnetic products for ferrous scrap recovery. When you have a look at level 2, now we're shifting into the non-ferrous. So for your typical auto shred, this is the rest of the material that's moving into your eddy currents. And many of you are familiar with eddy currents. They're ejecting non-ferrous metals. That is your Zorba product. And your Zorba drop fraction off of the eddy current is moving into your sensor downstream. So this sensor downstream is typically going to be, it can be as little as 1, but generally you're looking at 3 machines with performing different sorts in each step, and we'll talk about those in a bit. But these are the first 3 recovery levels, and you can see the equipment that's associated with them. What does it look like in more of a processing or flow chart standpoint? So we start out where you have, your shredder, your scrap that's using magnets as well for primary steel recovery. We've kind of simplified that into one block just for simplicity. And then moving into some sort of screening step, whether a trommel or a different screen setup, that's sizing the material appropriately to move into your eddy current lines. Your eddy currents are, of course, producing Zorba in your different size fractions. And then following this line here, the drops or the reject fraction off your eddy current moving into your ISS, KSS downstream. As a typical layout, you're going to have your first ISS firing on all your metallic, producing a metallic concentrate. And so your non-metals are going to be dropping out there. Your second step would be firing on large metals. Generally, you're producing a stainless steel fraction at this point. And then again, the rest of that material travels to an ISS or a KSS in this spot because you're going to be focused on ICW or insulated copper wire recovery. In this instance, on this flowchart, we've shown one line just for simplicity. In a real layout, it may make more sense to have a couple or multiple of these lines based on your grain sizing for the best performance. So we've touched on this a little bit, but let's talk about recovery keys. What are some of the key points for a good recovery step? So the two that I'm going to highlight here are liberating and screening. So of course we have incoming scrap material. In this case, we're showing end-of-life vehicles or automobiles. You can have anything really going into the shredder, but white goods are common as well. And it moves into a shredding step. And the point of this shredding step is to liberate the material. Ideally, you're going to have a piece that's a homogeneous piece of material. It's one piece of metal. It's specifically a copper piece, or it's specifically a brass piece. There's not attachments, for example, bolts in aluminum or a piece of copper tubing off a brass fixture. Ideally, you're liberating these so that the piece itself is homogeneous, so that it can react as you need over your separator. After shredding and liberating the material, you're going to move into the screening step. So at its base, the recovery is going to be best when material is liberated and it's classified. So there's the expression, no screening, no sorting. And what that means is if you try to run everything out of your shredder onto one eddy current, you're definitely not going to see peak performance and peak separation there. Material needs to be sized appropriately for any piece of sorting equipment to perform its best. So what does it mean to size material appropriately? The rule of thumb is a 3-to-1 ratio. So your largest piece on your belt is 3 times as big as your smallest piece on your belt. So if you're thinking about this in your current cuts today, so you have a 1-inch cut, maybe you're going to run 1 inch to 3 inch across an eddy current. This ratio is certainly more important on the finer side of things, so below 1 inch. When you're talking about doing sorts with material below 1 inch, you're going to want to hold to this ratio a little bit more. As you move larger than 1 inch per se, you can start stretching that band a little bit because material is easier to be detected. It reacts a little more similarly in that size band. So for this ratio, it's certainly not a guide you can get, or it's certainly not a rule, it's a guide. You can get good separation with a range that's larger than this, but ideally this is the 3-to-1 ratio that you're sticking to. We've talked a little bit about the recovery products, but let's just take a look at them. Zorba on your left, a non-ferrous metal mix, stainless steel at the top, and then ICW package on the right there. For some locations and some yards, these are finished products. These are their finished sellable products that are going out. For others, these are interim products. So if they're your sellable products today, you might be thinking, well, what happens to them? Where else are they going? And we're certainly going to cover that because that is part of the refinement process. So again, we're going to go back to this chart that we looked at earlier, and we're going to talk about the bottom half. These are the refinement steps, levels 4 through 6. As you can see across the top there, what we're looking at is X-ray technology. We're looking at X-ray transmission technology, we're looking at X-ray fluorescent technology, and we're also looking at LIBS, laser-induced breakdown spectroscopy. So the different levels, the refinement levels, level 4, which we're talking about here, is Zorba separation into light and heavy metal concentrates. We can also, in the second step, separate cast and rod aluminum. In level 5, we're looking at separation of non-ferrous heavy metals. So this is going to be an XRF application primarily. And I should take a moment to say that the X's in parentheses, there's capability with that technology. So for example, here in level 4, when you're talking about Zorba separation to light and heavy metals, this is primarily an application for XRT, but there is some capability with XRF and libs as well. For level 5, this is primarily an XRF application, but again, some capability with libs. And then level 6, element-based sorting of aluminum alloys. This is going to be primarily a libs application. So this bottom half of the chart are your refinement steps, and we're going to walk through the refinement steps in a similar fashion as we did with the recovery steps. So level 4 here, what you see is a KSS XRT. So the KSS is a combination sensor sorter platform that offers you a 3D, a laser and camera, along with a color camera, an induction sensor, and then of course your X-ray bridge. For this platform here, we're looking at an X-ray transmissive, XRT. You can also get a KSS XF, X-ray fluorescence. For KSS XRT, this is really your first refinement step. The KSS XRT is going to lead the way. X-ray transmissive is a through technology, meaning that it's not just surface detection, it's actually sending energy through the piece so that we're able to detect high density spots in the piece. And that allows us to more accurately sort and classify pieces that may have some of those inclusions that we mentioned earlier. Level 5, separation of non-ferrous heavy metals. That is an XRF, X-ray fluorescence application. Here we see our SHUTEC, which is optimized for the 3-inch and down fraction, down to 5 millimeters. And this is called a SHUTEC because it's a chute style design where material is actually detected and ejected out of free fall. And we'll talk a little bit more about some of the trade-offs in that in a later slide. Then finally, level 6, what you're going to see is separation of aluminum alloys by element. This is our linear sorting system, LSS, equipped with libs. So again, we're talking level 4, separation of Zorba into light and heavy metals. Second step, separation of cast and sheet aluminum. We'll also talk about a special sorting step for magnesium. Level 5, separation of heavy metals. This is an XRF application. And then level 6, libs, separation of aluminum alloys by element. So as we did earlier, we're going to have a look at a flow chart, how this could look in a plant. So on the right side, we have our recovery step. And to try to simplify this, we're going to let that fade away and we're going to look at the refinement line. So it's important to note because we're going to take a look at more detailed layouts later on in the presentation. But when you see multiple machines, that could be multiple machines in line, or it could mean batch processing or sending the material back across a single machine. So when you look at our refinement downstream, how is it laid out? So we have our Zorba here today. That's a product of our recovery process off the eddy currents. And we're going to send that into our first step, XRT. This sort is going to be separating heavy metals from light metals. So here's your heavy metal product, and we're going to follow that flow chart in just a second. But on your other product off this first step will be your twitch, your aluminum fraction, this mixed aluminum fraction. This can go into your second stage, your second sorting XRT, which is going to be separation of cast and sheet or cast and wrought. And then a final third step could be concentrating your magnesium content or separating out your magnesium content. So those 3 XRT steps are your typical refinement flow. When we look back at this heavy metal fraction that we produced off the first stage, XRT, now this is going into your XF sorting. Obviously, we covered earlier that XF sorting is separation of heavy metal mix. So now you see the heavy metals going into the XF sorting line. And at this point, you're doing commodity sorts. So you're looking for copper and precious metal. You may be sorting for zinc. You may be sorting for brass, chromium nickel plated, lead, stainless, etc. You can feed Zurich into this XF line, and we're going to take a look at that. So this is a general layout of what refinement looks like in a flowchart standpoint, and this is really taking your typical recovery products, Zorba and Zurich, and talking about how we refine those further. So as we did for recovery, we'll talk through a few of the keys for refinement. Screening. Again, yes, it's again because screening is equally important here, if not more so. The different Zorba fractions that you're producing today, say if they're combined into a single outfeed conveyor or they're dumped in a bunker together for simplicity. If you're going to be classifying those, or if you're going to be sorting those further, you're going to want to classify them again. You're going to want to screen them again. They might need to be screened differently. It might make sense for your throughputs, for your working time. It might make sense to classify them differently. So screening again is an important step. It's also important for refinement to remove non-metallics as much as possible. When you're talking about reaching these high quality furnace ready products, having non-metallic material in there is going to lower your purity. That needs to be removed if at all possible. As well as a final refinement key is controlling your minimum sizing. So we're talking about screening, we're talking about sizing. What does controlling your minimum sizing mean? Well, as I mentioned, the Schutek's optimized for 3 inches and down to 5 millimeters. So I'm sure many of you have this fraction size that you call and down. It's 1 inch and down or 3/4 inch and down, whatever it may be today. But actually how much of your particles are in that and down fraction? How many of your particles are below that 5 millimeter where the Schutek is really capable? So if you can control your minimum sizing and remove those dust-like particles and limit the number of objects going to the sensor sorter, that can be a big advantage as well. Let's have a look now at some typical XRT aluminum refinement products. So we mentioned the second stage sort of cast and sheet aluminum. So here we see our sheet aluminum, rod aluminum on the left, and we have our cast product on the right. We'll do the same thing for XRF. Look at some of these XRF refinement products. At this point, pick your elements: copper, zinc fraction, brass fraction. A fraction that you may not have seen or may not have paid as much attention to would be the precious metal concentrate. So in this fraction, you see that we have coatings, we have, you'll have coins in this fraction, you can have silverware in this fraction. This PM concentrate is where we've seen a large value with XRF, particularly the Schutek, and we're going to cover that in just a bit. So now let's have a deeper look into refinement and some of the highlights and what that means for these products. So of course, we'll dive right in with our chart again, and we're going to look at Zorba separation as well as cast and sheet separation. This is primarily an XRT application. Now, let's say you have a specialty focus on profile or extrusion scrap. This is the area of in-feed material that you specialize in. Here's some examples of, we're going to show the same melt data. Here's some examples of the in-feed material. For this fraction, what you're really talking about, some of your typical concerns are steel, ferrous inclusions, zinc attachments, as well as organics like wood and then rubber in some of these pieces as well. But with XRT, we're able to sort these in the same fashion. Again, you can see examples of the sorted profile or extrusion scrap, where we're ejecting on the right the cast, the heavies, any boards, basically anything that's not meeting our rot criteria. So now let's talk about a special task with XRT, which is magnesium sorting. I mentioned it earlier, but free magnesium can be anywhere from say 0.5% to 3% or so in typical ASR scrap. And when you look at a pile, if you don't have a trained eye for it, you might not even recognize it. So what we see here is some pieces marked in yellow. So these are the ones with the yellow X's. And what you can do with our XRT technology is you can, once you detect the magnesium, you can send it appropriately with the product that you want. So for example, you could send it with your sheet product, you could send it with your cast product, or you can run solely to sort out the magnesium so that you're completely removing it from your material stream. And obviously, how you do this is a balance of your number of machines, your processing time, what you desire, your outlets for the material, etc. But the important thing to know is that XRT can detect it. We have that capability, and we're going to talk about that here. So what are we looking at? We see 3 different pieces. We have a piece of magnesium, we have a piece of sheet aluminum, and then we have a cast piece of aluminum. So when we look at this piece of magnesium, we see that it's very high percentage mag and low percentage aluminum. When you look at the sheet piece of aluminum, it's very high percentage aluminum with barely anything else included. When you look at the piece of cast, you see, of course, the heavy elements, the silicon, the zinc, the copper. On the visual scale, which is what this first column is, there's really not much difference. Of course, those that are familiar could probably pick these up and know exactly which is which, but that's not reasonable for a sorting task or a sorting step. So we need to use the XRT. And when you look at it, even on this image, you don't see a major difference here. But as we move into the multi-layer XRT image and we look at the classified XRT image, what we see is that using the mean density curves that we have, we're able to detect the dense spots. And based off the curve, that's what's determining what is the dense spot. So here, we're able to see that this is a very light piece, that it's mostly magnesium, and we can detect that. When we look at the sheet piece, of course, we see a little bit more dense spots, those red spots there. We see that it has some denser spots. Then the ultimate piece with the cast and seeing all those heavy elements, we're able to detect that heavy metal concentrate in there and easily identify and separate the magnesium from the sheet from the cast. So we're going to go back to our chart again, and we're going to have a look at level 5. Level 5 is separation of non-ferrous heavy metals, which is primarily going to be your XRF application. And we're going to start with a Zurich feed or a stainless steel purification. So say you have this Zurich fraction today, you can run it over an eddy current to capture your remaining Zorba that was left in there. And now you have this stainless and wiry mix. So in general, you could use the KSS with a laser and induction sensor to eject out your soft metals, generally your wires. Maybe this is an in-feed for a granulator line, a chopping line, etc. And then you take that predominantly stainless fraction into your KSS XF, and it's going to upgrade your stainless percentage. Based off your in-feed concentrate and the in-feed product to this process, it may not look exactly like this, but effectively, based on that in-feed to the XF, you can see a high upgrade in stainless steel percentage. In some instances, with a solid in-feed and a good pass over the XF, we've seen 99% plus stainless. Aside from stainless upgrade, what we're going to look at as well is the heavy metal separation. So on the left, what you see is a mixed heavies fraction, maybe off XRT, maybe off heavy media system. On the right, you see a heavy metal mix off IBA, an IBA fraction. And the important thing to note in these fractions is that they do contain precious metals. And when you're using XF, you want to recover those, you want to identify them. So for each different material stream that's coming in, you see different precious metals in that grouping that are common. Of course, there are exceptions to any rule, but here are some of the common precious metals that you look for and see in the different incoming streams of E-scrap incinerator bottom ash, IBA, or ASR. And we're going to focus on just this copper fraction that's highlighted. So for E-scrap, you see, of course, the silver and the gold and platinum and palladium. This is a lot in, you see this in your board content, you see this in copper coatings, and this is very common for E-scrap. When you look at incinerator bottom ash, you're going to see more loose gold and loose silver. That's what the asterisks are there to denote. So this may be things like jewelry or the classic silver spoon that we pull out of the stream. This is going to be more loose, kind of approximate maybe 50% of the gold and silver content out of IBA is that loose fraction. And then specifically for ASR, when you look at that, you see a lot of silver. And this is silver that's used in coatings, platings, mostly on the electrical connectors that are used in the autos industry. So now let's have a look at a more detailed XRF flow chart. We're going to start with the fine grain size, so 5 to 75 millimeter. Like we said, the SHU-TEC is optimized for this fraction, so this is what's going to be included in the flow chart. Your in-feed material is a Zebra heavy metal mix, perhaps off XRT or heavy media, maybe an air table, and it's feeding in to your first step. And in this example, we've shown that zinc is going to be ejected first. That's most likely because zinc was their bulk composition, and it makes sense to eject zinc first. But it's not so important that you focus on the commodity sort order in this flow chart. What's really important is that you understand that you are doing a commodity sort, and we will set this up and strategize with you to do the sort order that makes sense. They can easily be swapped around. It's easy to swap the program on our machine interface, so any operator can do it with just a simple understanding of the in-feed material and the program they want to select. So don't get caught up in that, but just realize that these are the typical sorts that you'll see across an XF machine. And again, it doesn't necessarily mean that you need 3 machines in line. You can always refeed the material in batch processing across the same machine with a different program. But with all that said, typical layout is something like this. You've ejected your zinc fraction. Your material is continuing on to your second stage for ejection of copper and precious metals, and then the rest of it moving on to your third stage, brass, and say your lost precious metals. So these are just an example of a flow chart. When you look at the larger fraction, coarse grain size, say 15 to 130 millimeter, half an inch to 5 inches or so. What you see is the exact same flow chart. So it's, for many you may not have noticed yet, but this is a different machine. It's the KSS. And the KSS is going to have some advantages in your larger grain size. But what you see, of course, when you look at this band, 15 to 130, and you look at 5 to 75, there's a lot of crossover. And so what does that mean? How do you select the right machine for your application? Well, that's what we're here for, to talk about your ultimate goals and sorting products and what you're looking for, and we can help you decide that. But here is sort of a general layout of why do I choose one versus the other. So I won't talk through all these in specific detail, but like I mentioned, SHU-TEC is optimized for the less than 3 inch fraction, specifically below an inch, 25 millimeters or so. The SHU-TEC is going to have a higher advantage with its the higher resolution that we've built into that machine. On shape, when you're talking about a very mixed material stream with a bunch of different object shapes, the laser detection on the KSS provides advantages there. Rolling material, you see, you may desire the SHU-TEC, so with the design of the SHU-TEC, obviously objects falling through the machine being detected and ejected on a free fall, there's no brass rolling on the belt, there's no capability for pieces to roll like that and mistime your valves with your detection. So we see SHU-TEC have advantage with that, and definitely see improvements in brass sorting there. So, and like I mentioned, wide grain size and capacity, we're moving through those depending on your size fraction. These can vary. So, in general, we can help you decipher those and talk through those. So overall, I hope this was informative. I hope this was enjoyable to learn a little bit about refinement processes, how we think about it, what refinement is, and potentially has you thinking about how this could work for your yard. Ultimately, the goal is to get the maximum value out of your material stream and create those furnace-ready products. Please reach out to us. Here's some of our contact information. Hopefully you know your local STEINERT territory manager. Reach out to them. We would be very happy to talk with you in more detail about how refinement solutions could make sense for you. Thank you for your time and attention. I hope you have a great rest of the day.